Thank you, Shannon, for the introduction, and thanks to everyone who has attended today. Hopefully, you'll gain some insight into how carbon and chlorine affect treatment decisions, as well as how the instrumentation that we're going to show today can help you with your processes in these analyses. So today's webinar centers around two important elements, those being carbon and chlorine. The topics that I'll cover today include how the presence of carbon-containing compounds in source water drive regulations and treatment decisions. Additionally, also how the use of chlorine drives additional regulations and other treatment decisions. I'll also discuss the relationship between carbon and chlorine for the formation of the disinfection byproducts. Lastly, I'll present the fundamentals of available online instrumentation that can be used to monitor the effects of these two important elements and assist in water treatment processes and decisions. Just a second. There we go. In the universe, only hydrogen, helium, oxygen, neon, and nitrogen are more abundant than carbon. No one really knows when carbon was discovered, but we could attribute that to the first person who ever handled charcoal from a fire. And that was probably a very, very long time ago. Carbon is an extremely diverse element that forms very expensive materials like diamond, to very inexpensive material like graphite that's used to make pencils and also used as a lubricant. However, for our discussion today, the last statement is the most important. When we think about contamination in water and removing that contamination, we must be concerned about carbon-containing compounds. Carbon as organic carbon or total organic carbon is an important water quality parameter. In all cases in which water is contaminated, many of the contaminants are carbon-containing compounds. These compounds may naturally exist in the environment. For instance, the fulvic and humic acids are formed during the decomposition of organic and plant matter. Other carbon-containing compounds from industrial or municipal waste can also contaminate water. The first step in water treatment processes is the removal of these compounds. The determination of TOC affords a quick and easy way to measure the amount of organic material that must be removed and the amount of organic material that has been removed in the treatment process. Water treatment source water may have TOC levels in the 2 to 8 part per million range, and TOC discharge targets in the 1 to 2 ppm range or less. Municipal wastewater treatment plants may have TOC levels in the 100 to 200 ppm range, with discharge targets less than 10 ppm. Strictly speaking, TOC is not regulated in the sense of specific limits, say, for certain elements or other compounds. However, there are congressional acts and regulatory agencies that require TOC monitoring. These include the Safe Drinking Water Act, the National Pollution Discharge Elimination System, and the Resource Conservation and Recovery Act. For instance, the Safe Drinking Water Act gave us the disinfection byproduct rule, among other things. MPDS, BOD, and COD or TOC determination in wastewater. The RCRA gave us standard method 846 for monitoring wells around landfills and other contaminated sites. Also under the Safe Drinking Water Act, the National Primary Drinking Water Regulations were established. Title 40, Parts 141 and 142 are the most relevant sections for our discussion today. Part 141 establishes the regulations. Part 142 covers the implementation of those regulations. It is beyond the scope of this webinar to cover all the details of Title 40. However, there are important sections that are applicable to our discussion about carbon and chlorine. These are Subpart H systems, the groundwater rule, and Stage 2 disinfection and disinfection byproducts rule. Subpart H systems are public water systems using surface water or groundwater that is directly influenced by surface water. The groundwater rule applies to all other systems using groundwater, except when that water may be influenced by surface water. In the section on chlorine, I'll cover the implications of the Stage 2 disinfection and disinfection byproducts rule, which will come in just a little bit. This chart shows the required TOC removal for subpart H systems. As you can see, the source water of TOC in the range of 2 to 4 milligrams per liter is very typical. As you would expect, as the source water TOC concentration increases, the percentage of removal also increases. However, in many cases, a higher percentage of TOC removal beyond the required targets may also be beneficial or necessary to prevent the formation of disinfection byproducts in the distribution system. In this slide, I show the points in the treatment process that should be characterized for TOC. Of course, as the previous slide showed, the two most important points are the influent and effluent, so that the TOC target removal, the targets can be reached and monitored. However, to adequately map the entire process from the plant to the distribution system, all of these points should be sampled and monitored for TOC. In addition, the mapping of the distribution system should also include residual chlorine and total trihalomethanes. TOC and THM precursors. This is a topic recently that I've found remarkably interesting. Even though we are using successive steps in a treatment process to remove carbon, there have been a number of studies that show that the residual carbon that persists through the treatment process becomes more reactive and favors THM formation. And the consequence for treatment processes could be this, in that it implies that in addition to what's currently being used in the process, that additional treatment steps may be necessary. It also seems to suggest that additional measurements may be necessary to actually characterize these compounds as they move through the treatment process. UV measurements at wavelengths 254, which is very common in many treatment processes. In addition to that, other information could be gleaned at wavelengths of 280, 472, and 664. for instance. So what this seems to suggest is that the compounds or the molecular structure of these compounds is changing as they move through. And it has been shown that these become more reactive in their reaction with chlorine. So now I would like to discuss how an online TOC analyzer can be an effective tool in managing organic carbon removal throughout the treatment process. The picture you see here is of the TOC 9220 process TOC analyzer that is now available from YSI. But before we talk about the instrument in particular, let's just go over a few things about TOC analysis in general. This shows the basic building blocks of TOC analysis. Every TOC analyzer essentially must use these 4 steps. In step 1, there has to be some mechanism for getting the sample into the analyzer. Some instances that might be a syringe, could be a sample loop. In terms of laboratory instrumentation, that could be an autosampler. The second step is oxidation. All TOC analyzers analyze carbon in any form by first converting it to carbon dioxide. The methods that are available today include combustion, heated persulfate, UV persulfate, and 2-stage oxidation. The model 9220 will use the heated persulfate technique to oxidize organic carbon to CO2. The next step in the process is to detect that carbon dioxide. This is usually done by either a non-dispersive infrared detector, NDIR, or membrane conductivity or direct conductivity detectors. And then lastly, we have to do something with the data that we just generated from the analyzer. Of course, that's usually displayed locally at the analyzer, could be printed out to some device, and in most cases stored somewhere either on a local computer, internal computer, or a SCADA system. As I mentioned, the 9220 uses the technique of heated persulfate. The persulfate reaction is based on a wet chemical oxidation using sodium or ammonium peroxodisulfate, also simply referred to as persulfate, and orthophosphoric acid as reagents to convert any compound containing carbon, including organic carbon, to dissolve CO2 within a reactor at 98 degrees C. The 9220 uses sodium persulfate and phosphoric acid. Sodium persulfate is highly soluble in water and forms several radical species that act as strong oxidizing agents. The chart on the right-hand side of the screen shows the redox potential of ions from the highest, being fluorine at 2.87 volts, to the lowest, hydrogen, is 0. The equations on the left-hand side of the screen show the reactions that take place when persulfate is dissolved in water and activated by heat. In addition to the formation of hydroxyl radicals, other very highly reactive radicals are also formed. These include the sulfate radical and the persulfate ion. All of these species combine to make persulfate a very powerful oxidizing agent. The exact mechanism for the oxidation of organic compounds using persulfate is not completely understood. However, it's believed that radicals, such as the hydroxyl radical, cleave the carbon-carbon, carbon-oxygen, carbon-hydrogen bonds, and also initiate a series of other oxidation reactions that leads to the ultimate production of carbon dioxide in water. In my slide here, I show fulvic acid. Fulvic acid, along with humic acid, probably accounts for between 25 and 75% of the organic matter in soils, and another substantial part of the organic material in natural waters. This is a generic version of a water treatment plant and shows the typical placement of an online TOC analyzer. In reality, although we would probably like to do it, it doesn't require two analyzers in most cases, or in probably all cases. The samples are plumbed to the analyzer. As we saw in subpart H requirements for TOC removal, the influent to the plant and the final effluent must be monitored for compliance to TOC removal targets. I've also taken the liberty here to show some additional information that's available, or products that are available to provide other important parameters such as pH, possibly phosphorus as well, and chlorine for monitoring chlorine if you're using chlorine as the disinfectant. And then lastly, or almost lastly, the regulatory methods. And while this may not be a completely exhaustive list, I do show most of the relevant methods that are on the books today. I will only touch on a couple of them. I highly recommend that analysts and other stakeholders take the time to become familiar with the methods that pertain to various TOC techniques, or to the TOC technique that you might be using. Remember that these methods provide guidance. They are not rules in and of themselves. They are available to help the laboratories and operators achieve satisfactory results, and also for proof to a third party if you are making these measurements. The importance of the methods is that they provide guidance on which TOC technique may be best suited for your application. And as far as the Model 9220 online TOC goes, that instrument conforms to EPA 415.3 and standard method 5310C. So now let's just take a quick look at and review the components of the Model 9220 and how it performs this measurement. The instrument, of course, has to have some way to display the results. And on this instrument, that would be a 7-inch VGA touchscreen display, which serves as the interface between the operator and the instrument. On the right-hand side of the instrument, and the component that's used to bring sample into the instrument, is a syringe. This also acts as a TIC removal chamber. According to standard method, TIC, the inorganic component in all water, must be either measured or removed. In our instrument, the TIC will be removed by the addition of phosphoric acid to the sample aliquot. The sample is reacted in here. The CO2 that's generated is then vented overboard. After that step has been completed, the sample is then transferred to item D, the TOC reaction chamber, which is an isothermal chamber operating at 98 degrees C, again, according to standard method. There it reacts with persulfate for a predetermined amount of time. All the organic compounds in the sample are then converted to CO2. That CO2 is then vented out of the reaction chamber and into the NDIR. This instrument uses a non-dispersive infrared detector that's behind this box that you can't really see. And the bottom part of the screen here, there are other components that are important to the operation of the instrument. This instrument does not rely on pressurized or fixed gases, cylinder gases. An onboard pump will pull room air through what we describe as the process gas module. It will scrub this of any moisture and CO2 and then push it back into the instrument and serve as the carrier gas, which moves the CO2 from these various components into the detector. And then additionally, this instrument has 4-stream capability, and the devices where the customer would plumb into are shown at the bottom. So each one of these would be an individual sample that the instrument can monitor. And then lastly, we need the reagents. So there are containers for sodium persulfate and phosphoric acid. In addition, the instrument does use DI water for various purposes, mostly for rinsing the sample chamber in between measurements. A quick tour through a schematic diagram, how it works. As I mentioned, sample is drawn into a TIC, through the syringe into the TIC removal chamber. Acid is added. The CO2 that's generated in that reaction is vented overboard. The TIC free sample is then transferred to the reaction chamber, which is held at 98 degrees C. Sodium persulfate is delivered through the persulfate pump. CO2 from oxidation of organic compounds is then measured directly by the NDIR detector. And these are just some of the high-level specifications of the instrument. Again, it uses the principle of heated persulfate oxidation. It conforms to USEPA 415.3, standard method 5310C. A couple of comments about the measurement range. The standard range of the instrument is 0 to 25 parts per million and adjustable up to a maximum value of 100 parts per million. However, if a lower measurement range is necessary, say 0 to 5, 0 to 10 parts per million, whatever that happens to be, or whatever you might happen to want it to be, then it's as simple as selecting that range, calibrating the instrument to that high concentration standard, and then operating it from that point. Limit detection currently is 15 parts per billion. Again, as I mentioned, it has the capability to monitor 4 streams, and a nominal cycle time is on the average of 6 minutes. Some of the advantages, again, the proven heated persulfate method, it's a technique that's been around for more than 50 years. A standard 2-year warranty. We do have 4-stream capability, compliant with the relevant methods, a rather low cost of ownership. There's nothing proprietary about the reagents you use. These are very common reagents that are easy available from us. They're available from a number of places, or in a lot of cases, they can be prepared by yourself. It also offers automatic validation and calibration capability if you choose to use that. I show one picture. This was the best picture that I had of the currently of this instrument run using all 4 streams. This is in a direct potable reuse pilot. At the time this was taken, the plant was still, or the pilot plant was still under construction, although the instrument is plumbed for all 4 streams. And we were monitoring the wastewater treatment plant effluent as the influent to this plant. and the initial step, which was optimization of the coagulant feed. The additional streams that were added later on in this process were biofiltration, and the fourth stream was GAC effluent after the other steps of the process had been treatment process had been done, and then the final step was polishing that sample through GAC. As I mentioned at the top of the webinar, this webinar was going to cover two elements. The first one was carbon. The second one is chlorine. So chlorine, let me just back up just a second here, sorry. So what is chlorine? Chlorine is a powerful oxidant that will kill or inactivate most pathogenic organisms that are harmful to humans and animal life. These could be bacteria, viruses, other dangerous microbes that we don't want to leave the treatment plant or exist in the distribution system. In its elemental form, chlorine is a gas. Under pressure, it becomes a liquid. At atmospheric pressure, it is in the gas phase, but it can be pressurized to create liquid chlorine. This is an important point because liquid chlorine is much more concentrated than it is in the gas phase. Chlorine was first discovered by a Swedish chemist, Carl Scheele, in 1794. He was the first to create pure chlorine gas by heating manganese dioxide with hydrochloric acid. He performed other research on chlorine as well and discovered it was also water soluble and could bleach things with it. But it wasn't until 1810 when English chemist Sir Humphrey Davy determined that chlorine was actually an element. And he named it after the Greek word chlorosis, which refers to the yellowish green color of the gas. But for our discussion today, what does chlorine do when we use it as a disinfectant? One consequence of using chlorine as a disinfectant is that it readily forms what are known as the disinfection byproducts. There are 2 classes and 9 compounds that are of particular interest to the US EPA. These are the trihalomethanes and haloacetic acids. These compounds are formed when chlorine reacts with organic carbon in the water. The 4 trihalomethanes and 5 haloacetic acids are shown on the slide. These include the chlorinated and the brominated compounds. So you might ask, well, we're talking about chlorine. Where does bromine come into this equation? The chlorinated compounds are a direct result of the reaction of chlorine with the organic carbon in the water. The brominated compounds are formed if there's any quantity of bromide in the water. In the presence of chlorine, which will be in the form of hypochlorous acid, hypobromous acid is also formed. Hypobromous acid is nearly 100 times more reactive than hypochlorous acid. So hence, a small amount of bromide in water can result in the formation of the brominated byproducts. From a regulatory perspective, the THMs are strictly regulated by US EPA. Therefore, to avoid any EPA entanglements, THMs must be monitored at the plant as well as in the distribution system. However, there are more important reasons other than just the US EPA regulations, and it is that the THMs do pose a threat to human health. Now back to the regulations. Stage 2 disinfection and disinfection byproduct rule defines what types of water systems are covered under the rule. As you can see from the slide, that's practically all water systems. It also defines systems that are not covered by the rule. This would be systems using UV light instead of a residual disinfectant. The MCLG is the maximum level of a contaminant in drinking water at which no known or anticipated adverse effect on the health of persons would occur, allowing an adequate margin of safety. As noted, MCLGs are not enforceable public health goals. However, they are a good goal to reach in process treatment as far as managing the formation of trihalomethanes. The maximum contaminant level, the MCL, is the highest level of contaminant that is allowed in drinking water based on cost-benefit analysis, and this one is enforceable. Locational annual average, or running annual average, LRAA, means the average of sample analytical results for samples taken at a particular monitoring location during the previous 4 calendar quarters. So each one of these is taken once per quarter, added up, divided by 4. Under the MCL, you see here the LRAA value of 80 parts per billion for the trihalomethanes, 60 parts per billion LRAA for the 5 haloacetic acids. This is the part that USEPA is most interested in. In addition to the LRAAs for both these compounds, the total distribution system monitoring points and monitoring frequency are determined by the size of the community and the type of water. So you see on the left-hand side here, subpart H for groundwater, the population size of the community, how often these must be reported per year, per quarter, and depending on the size of the distribution system, how many points must be monitored. The type of water, again, being subpart H in groundwater. So back to our schematic of a treatment system. I spoke about the TOC analyzers earlier being up in the front end. On the back side, where the water is going out of the plant, there's 2 possible best locations for an online THM analyzer. That would be before that water gets into the clear well, or depending on the particular circumstances of a plant, being primarily how long that water is going to sit in this clear well, how much organic carbon may be there, how much chlorine may be there, then that analyzer could be placed on the backside of the clear well before that water is distributed to the community. And then lastly, these are the approved analytical methods for the determination of the trihalomethanes and the haloacetic acids, as well as a couple of others, bromate and chloride. The US EPA methods primarily are the purge and trap GC mass spec methods, the most commonly used one being method 524.2. Some cases, larger municipal laboratories may have this capability. If not, then these samples would be sent out to another laboratory to perform this analysis for them. I bring this up because the instrument that I'm about to introduce to you uses techniques that are used in these methods for the determination of the trihalomethanes. And that would be the model THM 1100 online THM analyzers. As I put down here on the bottom of this slide, before we talk about the specifics of this analyzer, I'm going to first go over the basic principles of a purge and trap GC, because this analyzer is based on that technique. So, at a purge and trap, a sample is purged with an inert gas, transforming the purgeable organics to the vapor phase, where it is then collected on an absorbent trap at ambient temperature. So after that sample is purged, the trap is then heated, backflushed, and the compounds of interest are desorbed with an inert gas, in this case it would be nitrogen, onto a chromatographic column. The gas chromatograph is temperature programmed to separate these organics, which are then detected by most often a mass spectrometer, although the detectors could be a PID or an electrolytic conductivity detector or PID-FID. The instrument I show on the right-hand side is our auto sampler and purge and trap, which is very commonly used in the laboratory for the determination of the trihalomethanes. So quickly, how does a purge and trap work? Purge gases through a sample, creates finely divided bubbles which liberate the compounds out of solution. They're transferred out of this water matrix onto the trap, and they're captured and concentrated on the trap. In the next state, the desorbed state, the valve rotates, the trap is heated to rapidly thermally desorb these analytes. The carrier gas transfers the analytes onto a GC column. Then the purge and trap drains the sample, the pathway is rinsed with clean water, and gets ready for the next sample. And now let's just talk about the THM 1100 components and its operation. The THM or THM 1100 operates very similarly to the methods that are used for EPA compliance for these compounds. I'll start down at the bottom. This valve assembly at the bottom is what handles the sample coming either from the process or from a grab sample reservoir, which is used to calibrate the instrument. After the water flows through here, it is then transferred into a sparge vessel, which you see on the right-hand side. Again, according to the principles of purge and trap, gas is then introduced into this sample, which is held at 35 degrees C, and then transferred over to the trap, which is sitting right behind this fan assembly, which is used to cool it between measurements. It's a little bit difficult to see. It's right through there. The analytes are absorbed onto the trap. After that phase is done, then it is backflushed. The compounds are then introduced onto the front end of a GC column. In this case, it's a 12-meter DB1 column. And off the column, finally, onto the detector. Lastly, on this instrument, all the data is stored on board with this PCA SD card you see over here in the corner. So this does follow all the principles of a purge and trap GC. And some of the high-level specifications for this instrument, again, the operating principle is purge and trap GC. It uses a slightly different measurement technique as a detector, and I'm not going to go into any detail about this particular detector in this webinar. It has a range of 0 to 240 parts per billion and a limited detection of 1 ppm compound. Other highlights of it is the sample processing time is under 25 minutes, which is pretty quick for this type of analysis and these types of compounds, with 60 minutes minimum between cycles. We only do one stream, and the instrument does not require any reagents. Again, we're desorbing these compounds directly off a trap and then onto a detector. And it does have grab sample capability. So in summary, total organic carbon is an important water quality parameter. The EPA has clearly defined TOC removal targets for water treatment plants that fall under 40 CFR. Organic compounds or THM precursors can exist throughout the treatment process, even when the TOC concentration is relatively low. I've shown that there have been numerous studies that show there is a direct correlation between TOC and formation of byproducts when chlorine is used as a disinfectant. This is particularly true for the trihalomethanes. Stage 2 disinfection byproducts rule sets strict maximum contaminant levels for both the trihalomethanes and the haloacetic acids. Although I didn't mention it explicitly about the online THM analyzer, it's just the THMs that it can monitor. The haloacetic acids require a slightly different technique for determining those. But online instrumentation is available to monitor these important parameters in the treatment process. And with that, I would like to thank all of you very much for attending today. And at this point, I believe if there's any questions, we have time to entertain those questions for you. Once again, thank you for coming. And with that, I guess I'll turn it back over to Shannon, and we'll see if we can answer some questions for you.
Well, thank you, John, for that very informative presentation. We're going to move on to the Q&A next. If you have any questions, now is the time to ask. We do have a few we can get started with here. John, your first question is, what are the two most monitored points in a water treatment plant for TOC?
That would be influent and effluent. Because of the regulations that stipulate TOC removal targets in most cases, you have to know what's coming in, how much you're removing, and what the organic carbon concentration of that sample is going back out.
Thank you, John. Next question. Can we relate TOC measurements with BOD or use TOC values to estimate BOD?
Yes, you can. However, what that does require, let me just back up with the answer again. There are provisions within US EPA regulations that allow for the substitution of BOD with TOC. However, this can vary widely from state to state, and some of the ones that I'm familiar with may require correlation studies, both in colder, wet weather and warmer, dry weather. There's a appreciable amount of data that must be collected such that a correlation factor for your particular plant would have to be established before the local governing body would accept that as a substitution for BOD. But it is allowed, it can be done, and has been done in a number of places, but it does require a a significant, I would say it's probably a significant amount of work that must be done to establish that correlation factor. But yes, it can be.
Thank you, John. Let's see here. Do you have a target TOC value that doesn't cause formation of THMs?
I have not seen one personally. And that may again just depend on the source water and what might be in the source water. An example being in our community, I'm from College Station, Texas. That's where our office is located. And a colleague and I did a study a number of years ago of water from the surrounding areas. And what's primarily used here is groundwater. And well, all of what's used here is groundwater. There is no surface water in our area because there is no water treatment plant per se. But that groundwater is very low in TOC. In most cases, less than half a part per million TOC. But what it was relatively high in was bromide in the form of sodium bromide. And the water here is pumped up out of the ground, chlorinated, and then distributed. There's no additional treatment process that goes on. Consequently, and primarily in the summer, there are instances of very high total trihalomethane levels in this area. So again, there potentially could be a minimum. It would all depend on what's in that source water. But it's been my experience that even very low levels of TOC can result in a fairly significant concentration of particularly the brominated compounds, and then sometimes chloroform being the other one that's most readily formed.
Okay, can you tell us about some differences between the model 9210P and the 9220?
Sure. Again, if you look, if you can think back to the pictures that I showed of it, for one, the user interface has been improved. The graphics and software that control the instrument have been greatly improved. Some of the other pain points with the 9210P in terms of how sample and reagents are handled have also been improved. That means separation of how the sample is brought into the instrument, as well as the delivery of the reagents. That was simplified, improved in an effort to eliminate issues with onboard valves. Additionally, the reaction chamber was redesigned to be more efficient. There's a more efficient heater in it, in my opinion, which also improves the oxidation step. About the only thing on board the 9220 that is the same as the 9210P, and I'm thinking real fast through this, is the detector. Essentially, everything else has been redesigned and improved. Other slight differences now with 9210, if you wanted to, you could use all 6 ports of the sampler to run sample streams. That's limited now in 9220 to 4 streams. The other 2 are dedicated to high and low concentration reagents because we've added an automated calibration validation feature. So you have to have dedicated ports in order to do that. So, but in most cases, particularly in water treatment, I mean, you can get by with 4 sample points, 2 being the most commonly used. So direct to the question, practically everything on 9220 was redesigned and improved from 9210P.
Great, thanks, John. Next question. Can you set the THM analyzer in a distribution system?
Yes, you could. However, that might require some different utilities to effectively do that. Because of the nature of how the 1100 runs, the operating environment is very important because we are dealing with temperature being the most important factor. So if the analyzer was out in a location which was relatively temperature controlled by some way, and you can bring sample to it, then it could be done. But could you just stick one out in a distribution system in the open, unprotected from the elements, particularly the sun? No, that wouldn't be possible. But if you could house it properly and keep, again, the environmental portion of it being the most important part, then conceivably, yes, you could do that.
Okay, thank you. Does the 9220 require a maintenance contact? And do you have other authorized service providers?
Well, let me see how I'm going to pick that one apart. It does not require a service contract. We do recommend, however, a yearly PM, and as was the case with its predecessor, if local personnel are properly trained, because the PM requirements are very minimal on 9220, just as they were with 9210P. So if someone on site could be trained to perform the maintenance, then yes, that could be done in-house. Our company, because the 9220, it's a YSI product, however, it is will be serviced by the OI Analytical Field Service Group. We have our own field service group who will be handling this instrument. That doesn't mean that there won't be additional resources brought to bear in the future, but at the present, we internally handle all of the maintenance on that instrument. Again, it's very highly recommended for both these pieces of equipment that a yearly PM be performed, just to make sure that it stays in tip-top operating form. But is it absolutely required? No, we don't require it. We highly recommend it.
Okay, thank you, John. Looks like we maybe have time for one more question here. Let's see. Can the model 9220 determine total inorganic carbon?
No, it can't. The 9220, from a regulatory point of view, it's defined as non-purgeable organic carbon. That's allowed by 50-30-10C. as I mentioned during the presentation, TIC is removed instead of being determined. The reason being, for these applications that we do, the form of carbon which is of most interest is the organic carbon. Other instruments that monitor TIC do so because their operating principle requires that. There's two ways basically to operate a TOC when it comes to TOC and TIC. You measure all of the carbon and subtract the TIC, or you remove the TIC and just determine the organic fraction of that sample. Our instrument does the latter. It removes the TIC and then just measures the organic fraction of it, primarily because that is the form that is of primary interest in all these types of applications.